So, this talk is entitled Learning the Language of Failure. And there can be many interpretations to learning the language of failure. There can be interpretations such as, what are we talking about when we talk about software failures? Do we talk about personal failures? Do we talk about personal learning? And I'm going to dissect this title into its individual words before we get back to the entire theme of this talk again. So, the first thing here to look at is the word, here we go. The first thing to look at here is the word failure. And yes, during my entire career, I have been working on failures. Actually, I can also put a slide with the word failure and myself on the same slide, because I have been working on failures all along my career. Already as a PhD student, I had spent hours and hours and hours on debugging my own stuff, finding out why failures came to be. And my first attempt to this was building, together with a student of mine, Dorothea Lütkehaus, was building a graphical debugger. This is GNU DDD, which at the time actually was the first open source debugger with a decent graphical interface, so with help strings, and we also had a bit of visualization of data up there and everything. And this was tremendously popular at the time. I had a call for postcards, and I got a big bag of postcards over time from developers who simply were happy. So it was postcardware at the time. Today I would probably ask for Twitter likes or something similar. And that was actually my entry into the world of failures and debugging, and getting a first idea on how to, on where the problems were and how to solve them. A second attempt of mine, this was after my PhD. My co-workers and myself, in particular, my super apted master student Tom Zimmerman, who later became PhD student and who now is actually the head of SIGSOFT. We went and mined version repositories and bug repositories to see where the most bugs were in the program. That is, we collected the places where bugs were fixed and would then find out where those places where the most bugs were fixed. What you see here is a picture, a visualization of the Firefox, Firefox browser, specifically its version history, and each rectangle in there is a module, and the redder rectangle is the more security bugs were fixed in this module. And what you can see here is that in the lower left corner, we have this component named JS, which happens to be the JavaScript interpreter. And you can see that this is actually, among all the parts of Firefox, this is the place where by far the largest number of security bugs has been fixed over time. And such analysis, which now actually is called, well, this is an entire subfield of software engineering now, called mining software repositories. And at the time, this gave the first insights, the first automated insights on where the most bugs were and where it would make most sense to allocate quality assurance resources on. Well, JavaScript is not a big surprise here, obviously, but there's a couple of other counters here, say like the red corner up here in the left, where you can, where you will also find other parts of Firefox that have many security issues. And for the managers, in particular at Microsoft, whom we talked to, it's not so much the things that were the very first thing that came to mind, but actually those parts that are in the second row, which are just as important, but frequently overlooked. Another contribution my name is associated with in terms of failures is simplifying failure-inducing inputs. This is a very simple thing, actually. It's a simple technique for simplifying. Let me illustrate this. Here's a long input that causes a program to fail. We're having some vast arithmetic expression, and if we feed this into an interpreter of sorts, then the interpreter fails. And the challenge now is that you want to figure out which part of this large input actually is responsible for the failure. Because in general, there's only a small part of the input. here highlighted in black over gray, that is actually responsible. And what I invented was a technique which is called delta debugging, which automatically determines this failure-inducing subset. And the way that delta debugging works is it splits the input into smaller parts, initially say the half of the input, and checks whether the failure still occurs. So we take the first half here of the input. Unfortunately, this is not a valid arithmetic expression, so we take the second half of the input. And unfortunately, this is also not a valid arithmetic expression. And the nice thing about delta debugging is that it does not only split simply things in half, but then if both halves do not lead to a failure, then it takes out smaller parts of the input, such as this one. So we can take this early part out of the input and this fails. And then we can continue taking out smaller parts and more smaller parts and smaller parts until we finally get to, and all of this happens automatically, of course, with an automated test. And this is something we can easily repeat until we eventually find out the very simple failure-inducing input here, which still causes the failure. So these two techniques, actually, these two later techniques, delta debugging and mining software repositories, actually got me an ACM fellow for contributions to automated debugging and mining software archives, which tells you that you can actually make a career out of failures, simply looking into where the bugs are and what causes them, which I find somewhat recomforting over time. And let's now get back to the title of our work, The Language of Failure. So I have not talked yet about how we actually find those failures in the first place. That is, I've only talked about how to debug such failures, but the language of failure is actually something super interesting. So in the recent years, we have seen a tremendous interest in the technique of fuzzing. Fuzzing meaning that you create large inputs for a program automatically with the intent of seeing the program fail. This big string that we're seeing here, actually, this is not just a random, this is not just a string that I typed in. This is a string which was obtained via fuzzing. And fuzzing, yep, very simple. You create a big input and you find out whether the program crashes. Now, there's various flavors of fuzzing. The simplest fuzzing technique is to simply take and append random characters to each other, something like this, for instance. So we just take the alphabet of digits and operators and everything, and you can create quite a number of these. So that's actually not too difficult. But the problem is that your interpreter is, unless you have a bug in the parser of such inputs itself, your interpreter typically is going to reject those inputs because they are syntactically invalid. And so while initially fuzzing has been able to find plenty of bugs in the initial layers of a program where it's simply about processing inputs and putting them into buffers, which occasionally may overflow and likewise. If your bug is at a lower level in the program, meaning that you first need a valid input in order to get to these lower layers, because invalid inputs are going to be rejected in the first place, then you will not have much fun with dump fuzzing, because only 1 out of 1,000, 1 out of 1,000,000 inputs is actually going to be valid. And this is an enormous waste of time and resources, in particular CPU resources. And it's really, really not a very effective way of finding bugs in programs. Which is why I'm happy to see the fuzzing community adopting something that I have been proposing for quite a number of years now, namely to provide inputs that are syntactically valid in the first place. In order to do so, what we do is we need grammars. We need a specification of the input language. And yes, grammars are exactly what we need for that. A language as a set of inputs. And you know how grammars work, probably. Grammar describes the structure of an input. It consists of a number of expansion rules. These expansion rules tell you that the symbol on the left is being expanded into the symbol on the right. And the symbols on the right can be non-terminal symbols or sequences of non-terminal and terminal symbols. Non-terminal symbols will get expanded later on, and terminal symbols, well, will not get expanded later on. You may have seen grammars during your studies, mainly as a base for, well, first as a mechanism in formal languages and theoretical computer science. You may also have seen them in your compiler course as it comes to parsing inputs. For fuzzing, what we do instead is we use grammars as producers. And as a producer, that's actually pretty straightforward. You take a grammar and you can generate arbitrary many members of the language it represents with. So the way this works is you take the start symbol, here comes the start symbol, and then you apply these replacement rules by taking the symbol on the left and replacing it with the replacement on the right of the rule. So we just have exchange start via an expression. We have the expression. We randomly choose any of these expansions on the right. So we replace an expression by term minus expression. Now we have term and expression. So we take term. We again choose any of the expansions on the right. So term becomes factor, and factor then becomes an int.int, and an integer becomes a digit, and a digit becomes, and the other integer also becomes a digit. The integer becomes, well, let's pick a digit here, becomes 8, and the other digit becomes a 2. And we can continue this game now also with a second expression, on and on and on and on, which is actually fairly, easy to implement in a trivial way. It's a bit more complex if you want to have coverage of individual elements, or if you want to make sure that this doesn't expand ad infinitum. But what you can get here, right, if I keep on expanding expression, could be an expression like this. And lo and behold, this is exactly the big string that we have put into our interpreter in the first place in order to create the failure. So this big string, this big arithmetic expression, which is syntactically valid, was actually obtained via fuzzing with grammars. So the idea right now is that you take such a grammar and you put it into a fuzzer, and then this goes into a program under test of your choice. And how do we know that this works? Well, I know that this works because now, almost a decade ago, we did this for JavaScript. Took a JavaScript grammar, put this into a fuzzer, which is the langfuzz fuzzer, and the resulting JavaScript programs, we've put them into the JavaScript interpreters of the browsers at the time, which is Google Chrome or Firefox or Edge, and we found failures in all of them with plenty of generated JavaScript programs. And not only did we find the 3 failures, but actually we found failures all over the place. This was Christian Holler. He was my master's student at the time. He found more than 2,600 validated and fixed bugs. And in the first 4 weeks, he made $50,000 in bug bounties. $50,000 in 4 weeks. Since then, I've never had any trouble finding master's students after I told them this particular story, which is always great. And he's actually still running this today, and he still finds bugs in Edge, in Firefox, in Chrome. And if you have been using any of these browsers today, which is actually pretty likely, the reason why these things work as they should is, among others, very much grammar-based fuzzing. So, which is why I like the technique, which is why I actually like the technique so much. I get exposed to its result every day. So, the language of failure, if you do have a language specification that tells you how to get to failures, a language specification that gets you infinitely many inputs, this is enormously valuable for any kind of testing, but also for a number of debugging techniques, as we will see in a moment. We have plenty of ways to guide test generation here, grammar coverage, code coverage, probabilities, which I will not comment so much upon. But this is, I also like to point out that this is a technique which is very easily taught and very easily applied. So if your testing course does not yet have a lecture on grammar-based fuzzing, well, it's very easy to teach this in 45 minutes and 60 minutes, and you can even do some experiments with it. So let us now get to learning the language. And with learning the language, I'm looking at a particular problem that we have with grammar-based fuzzing, namely the problem. We have a grammar. From the grammar, we create a fuzzer, and then we feed this into the interpreter. The big problem is, where do we get the grammar from in the first place? And this is actually a big problem, because creating such grammars actually is work. You have to invest quite some time, quite some effort to get such a grammar in the first place. Which is why for a number of years now, we have been working on mining such grammars from programs automatically. And the idea is to take a program that parses inputs and to extract the input grammar from this very program. So here what I'm having is a small program that actually parses an expression. This is classical recursive descent. It parses an expression. It looks what the next character is going to be. So it parses a term. It looks what the next character is be. If it's a plus, then it parses the expression that follows. And we have a number of individual functions, each destined to parse a particular part of the input. And the interesting thing is that the structure of such programs corresponds to, well, obviously to the structure of the input, and therefore also to the structure of the grammar. So the idea is, can we establish a mapping between what we see, what's happening in our program, and can we create a mapping between the structure to get the structure of the input and therefore the grammar out of it? Now this is a weird problem which has hardly been addressed in computer science in the past years, because if you think about it, if you try to do this symbolically or statically, then, so if you throw a symbolic constraint solver, for instance, at a parser, the symbolic constraint solver is simply going to give up, or, well, at least it's not going to give you a solution in finite time, because a grammar is a compound of hundreds and hundreds of individual constraints. And constraint solvers that are not specifically set up for solving grammars cannot deal with that. So trying to get this out statically is, well, a pretty hard problem. It's an interesting challenge. Maybe there's somebody who finds a solution to that at some point. However, what one can do is one can do this dynamically, namely by observing how the program behaves while it's parsing an input. And that's what we've done. The key concept here is so-called consumption. We can, while we're executing the program, we can trace where individual characters are being processed in the program. We do this via a technique called dynamic tainting, which simply means that we observe all accesses to a character from the input in the program. And then what we can tell is which is the place, which is the method where a character was accessed last. And this is what we call consumption. Consumption means that there's a method which consumes a character. This means that the character was last accessed in this very method. And this concept of consumption is very interesting, because this gets us a relationship between individual characters, such as this one, and the method that actually processes them. So let me show you how we can use consumption to actually recreate a grammar. For each input character, as I said, we track where it's consumed. So we again have this minimized input, 1 times 8 minus 5. And now for every character, we track where is the method that we actually consumed it in. So the digits not very surprising, are being consumed in a method called parseDigit. This is the last method that sees them because it then transforms the digit into an internal representation. We also have a couple of operators. Minus would be processed in parse expression because parse expression needs, parse expression has a look ahead for the minus, and same goes for the multiplication, for which we do have a parse term. And let me rearrange these things just for clarity a bit. So we have this nice tree in here. And now this is one information we have, namely which individual method is associated with which character. But another information we have also is how these methods actually invoke each other, because in order to parse a term, you need to first parse a digit, and then you need to parse the operator, and then you need to parse a factor. And if we call in these call relationships, then we actually get a full parse tree in here. So parse term calls parse factor consumes the multiplication, parse factor consumes the parenthesis, and so on. Now, if we also add the other methods that are being called in between into the tree, then we get a full picture. And now we can replace these method names, parse something, by nouns, namely what is being parsed, and then we get these nice, candidates for non-terminal symbols. And this already is a parse tree as it would be produced by a grammar. And from this, we can now reconstruct the grammar that would have been used to construct this very parse tree. So what we can see in here is, for instance, that a term obviously consists of a term multiplied by a factor. So our grammar must have a rule to actually have that in its grammar. So we need to have a rule in there which says term consists of another term multiplied by a factor. This has to be in the grammar because otherwise we wouldn't get that tree out of it. And likewise, we also see that there's other expansions in our parse tree that a term becomes a factor. So there also has to be another alternative, namely a term can also become a factor. Likewise, we see in our parse tree, again obtained from the call relationship and consumption, that a factor can consist of an expression in parentheses. So we create a rule for our grammar that a factor consists of an opening parenthesis followed by an expression and followed by a closing parenthesis. This also has to be in the grammar. And a factor actually can also be an integer as an alternative, because we also see that in the grammar. And we have an integer, and this can be 1, 5, or 8. And this is now the grammar that we can get out of our parse tree. You see that this is not yet a grammar that covers all arithmetic expressions. It only covers those inputs that we have seen. But if we now go and create more inputs, namely say 0 plus 2, and create a parse tree out of that and feed this into the grammar, then this will automatically be added to the grammar, which now also contains the digits 0, 2, the addition operator, and here comes another one, which now finally completes the grammar. And with this, now we have seen every alternative in the parser, and this gets us the complete grammar. And this tool which we have here is called Mimid. This is a grammar miner by Rahul Gopinath, Björn Mattis, and myself. We had this at ESEC FSE this year. This is Mimid, and Mimid takes a C or Python program and a number of inputs, and out of these, it creates an input grammar, and this input grammar can then go into fuzzers to create more inputs for the program. It can go into parsers in order to parse existing inputs, maybe mutate them, put them into fuzzer again, but it can also go into humans. And the really nice feature about Mimid is since its structure is based on the program structure, and since its identifiers are based on the program identifiers, the resulting grammars are very much readable. So just as an example, Here is a grammar for JSON that we can extract from microjson.py. And what you see in here, this is, I never cease to have fun at that. What is a JSON? A JSON is a JSON draw. What is a JSON draw? A JSON draw is either a string, or it's a list, or it's a dict, or it's a number, or true, or false, or null. What is an array? An array is, we already had the opening bracket up there. Either it's directly closing bracket, or it is, let's look at the last line here, or it is a sequence of more JSON, of 0 or more JSON elements separated by a comma, and then coming up with a closing with a closing bracket. These are things. This is a grammar which you can. Well, this is a grammar which you can take and directly understand the structure of JSON, and you can go and you could even go and make this a textbook grammar. You can put this into a fuzzer of your choice. But the neat thing is you can also give this to humans to read, to understand. And the nice thing is that humans can even take this grammar and then expand it and toy with it. For instance, a human could go and add a couple of probabilities in here. Say we want plenty of dictionaries and only few lists, so we can say, okay, I want plenty of dictionaries, and then we send this to the fuzzer. You can also comment out individual parts just as you would do with a program and say, I want none of this, I want more of this, and everything. What you can also do is you can add rules on your own. So for instance, if you say, I want every second string to consist of the word drop table students, which is something you can do, and then you send this to the fuzzer. Then your fuzzer is going to create plenty of inputs that look like this. Namely, you have regular JSON input, except that, well, every second string consists of a SQL injection of drop table students into your string. So we have drop table students over here, over there, over everywhere. And yes, this is a very simple way of taking a set of valid inputs, making small changes to them, and try to bring in your favorite security payload in there. Very obviously, do not try this at home. Do not try this at your university. Do not try this anywhere else, except on your own programs, of course. If you run this on anything else but your own programs, you will suffer consequences, which will then end in your students table. Or not. Okay. Okay. I'm having a question here, and I will be addressing this in a second. So we already evaluated this for our paper. We evaluate this on a number of formats, going from simple arithmetic expressions. This is what we have here on the left. This is the calculator, going up to tiny C and JavaScript. So really complex languages, and the mind grammars are pretty good. So they generate 98% of the actual language. So we actually have very precise grammars in here. They also parse 92%, meaning that 92% of all valid samples, of all true valid samples, are actually being parsed correctly. And this even works on modern combinatorial parsers too. The question is, what we have here from Shangao is, how do you handle programs that are not well organized? Actually, what we find is that the largest majority of parsers actually are pretty well organized. The large majority of parsers falls into so the largest fraction of all parsers, about 2/3 of all parsers that we looked at, are actually recursive descent parsers, and these are written in textbook style. So this is, and these are very easy for us to extract. The next third is table-driven parsers. Table-driven parsers is something that we cannot work with because you essentially have, well, if you have a table-driven parser, you essentially have an interpreter integrated into your program, and this is something we cannot parse. However, table-driven parsers are typically generated from a grammar specification in the first place. So you already have the grammar specification. So this is not the highest thing on our priority. And the last fraction, but this is the fastest growing fraction, is modern combinatorial parsers, and we can handle these two. What we cannot do yet is mining binary inputs. Not so much because we're talking about binary characters. That's not the problem. But the problem is that binary inputs have plenty of semantic constraints, such as text lengths or checksums and others. And this is something which is, well, we can extract all the syntax from them, so that's fine. But extracting the semantics of these is actually a pretty tough problem. And this is work in progress on our side, and I hope to have a nice solution ready by the end of the year for that. Okay, so this is something we do. We learn such input specs automatically, accurately. And one thing that I didn't even mention is we learn from the given program only. We don't even need input samples. Didn't I just say we need input samples? That's right. But we also have a second technique, which is called parser-directed test generation. We had this at PLDI in 2019, which is a test generator that specifically is set to cover all the branches, of a parser. It is not sufficient to fully fuzz a parser, but it is sufficient to cover all the branches sufficiently such that we can mine a grammar from it, meaning that we can have you have a program that parses inputs. You have nothing else. Then our parser-directed test generator automatically creates inputs for that program, and these inputs together with the program itself then go into Mimit, which gets you an input grammar, and then this is what you can then work with. Question is, have you tested running this on a compiler? We haven't run this, say, on things like Clang or LLVM and like things, but we have actually tried this out on small compilers such as TinyC and JavaScript, and yes, these were very, very able to extract things. Actually, at the end of the talk, I'll give pointers on where to get these techniques and how to toy with them. Okay, so this is what we have about learning the language. So we can learn such languages automatically. We can use them, and we can use them for testing and fuzzing, and even feed them into humans. Something that I want to point out though today, and this is how we get to the final title of the talk, is how to use such grammars for figuring out why and how a program fails. And so we're moving a bit from testing and test generation into debugging. So we have seen how individual single inputs cause failures. That's all fine, and if you're in security research, finding a single input that breaks the program or gives you root access or whatsoever, if you have that, you're already in dreamland. You can file your CVE and get all the fame from your colleagues. But the interesting question occurs, if you do have such an input and you see that it causes a failure, the question is, are there other inputs for which such a failure actually can occur? And this is interesting from two perspectives. A, you want to fix things, and of course you want to come up with a fix that fixes not only this one single input, but you want to fix it for all inputs that cause a failure. And second, maybe in the past, maybe this is a failure that occurred in the past, and maybe there are other similar errors that are still in the program and yet incompletely fixed. So this is an interesting question, figuring out exactly under which conditions the program fails. And what we have done here is two very nice techniques that we have presented this year, which I'm very, very proud of, because this brings me back to my roots in debugging. So the idea is as follows. You do have this concrete input that you know that causes a failure, and you do have the grammar because now we have it, and you parse the input, and then you get again this nice parsing tree. And the question is, what can we derive other inputs that are similar and that give us way to an abstraction that also cause the failure? So say in this input that we have here on our left side, do we actually, so does the error occur only for this number 1 or number 8 or number 5, or does it only occur for this operator? So what is there? So which of these parts are actually placeholders for something that is more abstract? And if we want to answer this question, well, there's a simple way. Does the error occur for other integer values too? Well, we can find this out in our parse tree by simply replacing one of these integer branches by something else. And we can do so simply by pruning the tree and then regenerating, according to the rules of the grammar, regenerating an alternative to that. Mutating inputs on trees is really, really beautiful because you always stay within syntactic correctness in here. And now we take this mutated input and we feed this into the program under test, and let's assume we also get a failure here. And this is something that we can actually go and repeat again and again and again with various mutations of the input. So we have the original one, we have the mutated one, now we replace another int, and now we replace another int, and all of these fail. And now what we can derive from that is that we can actually have an arbitrary integer in this position, and it always fails. So by looking into a number of concrete instances, which we can generate this way, we can abstract things into these abstractions, which we already get from the grammar, namely by having these non-terminals as placeholders. And this is something we can repeat and repeat again and again with our program, and then we get the following pattern. And mind you, we get all of this for free because we have the grammar and we have the automatic fuzzer. All of this comes out for free. There's nothing that conceptually, there's nothing that you as a human have to do. You immediately get an explanation of why the program fails, namely the error occurs whenever a multiplication is used in conjunction with a minus. And not only do you get such an explanation of why the program fails, you also get you can also instantiate that pattern, and you then get plenty of test cases that replicate the failure and that also produce the failure, meaning that when you now fix the program, you immediately get a set of test cases that are set to specifically replicate the original failure, and all of these obviously now have to be fixed as well. And this prevents your fix from over-specializing to the one payload, to the one error that you see, but instead you now get all these test cases which your fix also has to handle. And we think that this is a great addition to debugging as we see it, giving you an explanation of the failure and also giving you extra test cases. This technique is called DD-set. This is a combination of delta debugging on sets, namely giving you a minimal explanation of the failure. And this takes a program, takes a concrete failing input, and takes a grammar, and it automatically produces such a failure. And when we say failure, I'm just having a Roland Yep here, this actually means any behavior that we can automatically observe. For a fuzzer, this typically means fuzzing, this typically means crashing or hanging, or if you're in ordinary testing, you need a predicate that tells you whether the program just produced an error or not. And we evaluated this DD set on a number of bugs in real life programs, and for 19 out of 22 bugs that we looked at, the concrete inputs could be abstracted into patterns, and these inputs were semantically valid. They reproduced the failures, and those patterns serve as diagnostics as well as producers, as we just have seen. But now we're not done yet, and because we've even gone further on that. So because you've seen this expression now, which is syntactically reduced to to the widest possible way. But see, the failure could could also occur for other operators. How about division, addition, whatsoever? And the failure could also depend on non-structural features, say the value of individual elements or the length of individual elements. And this is how we have then gone and put things even a bit further, namely by coming up with the failure may not depend on structural properties, but maybe on individual values. So what we have come up with is we have thought of, well, let us devise a number of input features these are features of input elements as we see them in the program input. And what we have here is, for instance, length, for instance, of individual elements. So we see a maximum length of integers of a value 1. The maximum value of all integers is 8. The minimum value for our integers is 1. The length of the entire start expansion in here is 7 because we have 7 characters, and we do have a few dozen more of such features. And all of these features could actually be related to the failure in question. And the question is, are there any of these features which correlate with failure? And this is actually not too difficult to find out. This is either, you can either frame this as a statistical problem, or you can frame this as a learner problem, or you can just frame this as a statistical learner problem. What we do is we take a program, we feed inputs to it, and then we get these labeled outcomes, pass or fail. And then from these inputs, we derive features. And we put these features into a learner together with the labels that we obtained from actually executing the program on these inputs. The learner then gives us a statistical model, a machine learning model, you name it as you like. And from the model, we can put in more inputs and more features, and the model is then a predictive model which predicts whether the input is going to fail or not. And actually, interestingly, this combination of taking features and feeding these into the model actually is an abstraction of the program as we see it. We're actually learning an abstraction out of the program. And let me illustrate how this works in practice. So we are having all these labeled inputs. We're having passing and failing runs, all with the inputs. And now we get these features out of these inputs. So for this input on the left here, for instance, we already see that we do have a 1 in there, a 5 in there, and an 8 in there. The maximum length of all integers is 1. So, and this whole thing is failing. And we have more features for the other input just as well. And we put these into a decision tree learner, and we use decision tree learner simply because they are easiest to debug for us. And they actually provide a nice explanation. They actually provide nice explanations on why they classify things as they are. And if we put these inputs together with these features in a decision tree learner, what we get out is that actually really happened. It tells us that the failure occurs whenever there is an 8 in the program input. And that's because, well, if you look at our labeled inputs in here, an 8 actually indeed only occurs in the failing run. There is no digit 8 in the passing runs. Mind you, this is one possible input. It could also be that the output is that the error occurs whenever the maximum length of an integer is less or equal than 1, then it fails. So what we have here is a classical situation. We have far more features than input. So obviously so the decision tree learner simply doesn't have enough material to come up with a good conclusion here. So the question is, we need more inputs, and we need more inputs to learn from. And this is something which is actually very nice, again, because given that we do have a grammar and given that we can run automated tests, we can actually generate these. And what we do is, from the model, we can generate more inputs to refine whatever we see in the model in the first place. And For this purpose, what we do is we take the decision tree, and for every path through the decision tree that leads in pass or fail, so the path here on the left side as well as the path here on the right side, we generate more inputs to see whether this actually holds. So if we do this for our inputs that we have seen before, so we have these 3 inputs in the first place, and now we generate more inputs. First, a set of inputs without the feature in question, going along the left branch, and then we generate more inputs with the feature going along the right branch. And there already you can see that since we again have passing and failing runs, that the original model cannot hold. We can learn a new model from that, and the new model now has more features to learn from, but also more inputs to learn from. And you will see that the new model is more precise than it was before. Now it looks at a multiplication and an expression, which actually is already more accurate. And this is something that we can repeat and again, and with every new iteration, we get more insights. And you can also think of this as an embodiment of the scientific method, with a model that we have here with a decision tree actually encompassing a hypothesis on why the program fails. And each of these new inputs that we generate here are experiments to validate or refute the hypothesis that we're seeing. And if you're repeating this a number of times, I think it's 8 iterations overall in our experiments, the final decision tree that we get is this one. And here we not only have 1 pattern, but 4 patterns actually that all are related to failure. So these 4 patterns actually occur with real. These 4 patterns actually make the failure occur, and we can very easily summarize these in one single sentence. Whenever we have a chance to apply the distributive law, that's when the program fails. And we can use these patterns and the resulting and these decision trees. We can use them as an explanation for the bug. We can use them as a producer of more test cases. But we can also use them as predictors, because we can also predict whether a failure is going to take place or not, simply by feeding new inputs and the features into the decision tree. And we call this approach Alhazen. Alhazen, for the Arab mathematician of about 1,000 years ago, of the Islamic Golden Age, who actually is credited to be one of the very first researchers, if not the first researcher, to systematically apply and characterize what we today call the scientific method, namely coming to a theory by means of observations, forming hypotheses out of these observations, creating experiments to refine or refute these hypotheses, which then lead again to new observations, which is how experimental scientists until the present day work in order to establish theories about the world as we see it. Actually, this was 5 centuries before the Renaissance scientists which actually rediscovered or independently rediscovered this concept of the scientific method again. And our Alhazen tool, which is named after Alhazen, takes a program, it takes a net set of failing and passing inputs, and it takes a grammar, and then it applies this cycle of taking observations, creating hypotheses, and refining these with experiments until it produces a model that takes inputs and feeds and produces passing and failing runs out of it, passing and failing outcomes out of it. And having said that, the passing and failing inputs in here can also come from a fuzzer. The grammar can also come from a grammar minor, which actually means that all of this, well, you take just the program and you feed it into Alhazen, and then you get a model that explains how the program works with respect to the predicate, the pass-fail predicate that you're looking at. And that's all you need to do. And then you get an explanation of why and when and how and the failure comes to be, and you get more test cases for the failure, all automatically. And yes, this also works well. We applied this on a number of, applied this again on a number of bugs, and it classifies inputs correctly. It produces about 70% of the produced inputs actually produce correctly caused failures, which is also nice. And these decision trees, the number of elements in the in the explanation is very small. Typically, we're talking about 5% of the entire language of input elements, which also already indicates that there is a substantial reduction in complexity going on. So rather than looking at all input elements, you can look at a small subset. And we are currently running user studies on how much these diagnoses and how much the resulting test cases actually help debuggers in debugging things more quickly and producing more and better fixes. Just to give you a couple of examples, here we have a grep crash and the resulting decision tree. Grep crashes when a particular option is used together with an empty search string. You feed in the crash, this is what you get out of here. So is there an option fixed strings, and is the length of the search string equal to 0? And if that's the case, then the program fails. Likewise, a nethack crash. Nethack crashes when a line in the config file has more than 619 characters. 619? Why 619? Well, that's exactly what Alhazen finds out, because it tries out longer. It tries out because this is what it observes when it tries to disprove this hypothesis of 619, then it goes for 600 and 700 and likewise. And since 600 doesn't fail and 700 fails, so it keeps on producing more numbers. It actually should be some sort of Newton iteration at this point, but already simply by combining random interactions and making them smaller and smaller again, it eventually gets to the conclusion that it has to be 619 characters. Don't ask me what is 619 characters. I'm not a developer of nethack, although I wish I would, although I wish I were. But these are simple explanations for failure causes, and again, you get these automatically as soon as your program fails. And I think you can concur with me, and there's quite some potential here for relief of programmers, providing them with far better diagnosis and far better means of reasoning about programs than what we have right now with interactive debuggers, where you're stepping through things and stepping things for ages and ages and ages and figuring out what it is. And here we directly give you an explanation on why the program fails. And if you're interested in these techniques, I'm happy to give you 2 pointers here. The first pointer is on fuzzing techniques, because I have been happy to lead a major effort compiling contemporary fuzzing techniques, including, of course, grammar-based fuzzing, in a book. This is the fuzzing book, and you will find, there's lexical fuzzing, syntactical fuzzing, and others. And there's also grammar-based fuzzing in there, of course. And last but not least, mining input grammars. This book is actually special because its chapters come as Jupyter notebooks, and they're actually executable right within your browser. So you can actually see the program and experiment with the program, with the whole implementation as it develops. And you can also download the code. You can simply say pip install fuzzing book, and then from fuzzing book import grammar miner, and then you can actually toy with these techniques on your own and see how well they work in your environment. And not only do I have a fuzzing book, but I am also happy to announce a new project today for the first time. And after the fuzzing book, I am now working on a new thing, which is called the debugging book, which puts together tools and techniques for automated software debugging. This is now 2/3 ready. It will go out to the public in February. Let's make this end of February, I guess. And here we do have, and this is where we are assembling plenty of techniques for automated debugging. This, of course, includes techniques such as delta debugging, but also program slicing, statistical debugging. Last week, I implemented automated program repair, and this also works. And this is also where you will be able to find techniques such as DD-set and Alhazen write in a form, in a textbook form, such that you can toy with them and such that you can experiment with these on your own. And if you're interested in these, follow me on Twitter. This is where I'm going to announce all these chapters as they come out one by one. So stay tuned. But now let me recap. What we have seen is learning the language of failure. We have seen mining grammars, that is how to automatically extract input specifications from existing programs and their executions. We have seen the patterns of failure, that is automatic patterns that explain you the circumstances under which an error occurs, along with associated test cases. I've shown you how to combine, how to extract such rules using machine learning methods such as decision trees to automatically learn under which circumstances a particular failure occurs. And finally, the Alhazen technique, which systematically refines such models, and where I see plenty of potential for further research, coming up with additional learners, coming up with alternate features, coming up with better refinements, integrating symbolic reasoning. There is still so much to be done and so many opportunities in here. So it's actually amazing, or that when I look at debugging, when I look at programming environments today, that we are still debugging things as 30 years ago, that we're still testing things manually. There are so many opportunities for automation, and these things can be set up in a way that it's not difficult or not impossible to deploy them on languages and programs of your choice. And I'm happy to work on this, and I hope to have given you some inspiration to work on similar things in the future too. That's all for today, learning the language of failure. May failures apply to the subjects that you experiment with, and let your own work be learning the language of success. Thank you very much for your attention, and I'm happy to take questions.
Thanks, Andreas, for sharing these insights. So I think there are some questions in the chat. Maybe there's a question from Zendong. Maybe you can go over that one. What difficulties do you face if you mine input grammars for normal programs? Okay, so like file processing. Okay, so I think
Yeah, that's an interesting question. The question is, what is file processing and how is it different from parsing? I think these are two words for the same thing that we're doing. Regular file processing programs. So whatever you're writing when you're doing some file processing, you're reading in some input, whatever it is, a CSV file, lines, whatsoever, and then you're decomposing these inputs into smaller parts. This is exactly the situation for which Mimid is set for. Mimid can extract the syntax of your input also for normal programs and file processing programs. One important limitation, though, is that it is limited to syntax of inputs, and it cannot extract the semantics of your inputs. Which means that if you do have syntactical constraints, meaning that A is composed of B and C and D, and B is composed and so on, these are things that we can mine. But things that we cannot mine is that, say, simple things like the next 2 bytes have to be the checksum over the next 300 bytes. Otherwise, this will be rejected because we cannot solve these, because we cannot automatically solve these checksum constraints. If you think of it in the extreme, you can have something like you can have something like the last 4 bytes the last 256 bits need to be an SHA hash over the rest of the inputs, and then obviously we will not be able to extract that, nor will we be able to synthesize that. Otherwise, we'd be able to break passwords and break signatures and everything. So these semantic constraints is not something that we can mine. Or at least not automatically to the same extent as we can as we can track the syntax. But these are things that are not very difficult to add afterwards, because you can add specific semantic generator constraints to a grammar, and this is also covered. This is also covered in the fuzzing book, by the way. And for simple constraints such as checksums and lengths and others, we are already working on extracting such constraints automatically.
So for file processing, actually, so there was a former student of mine, you know him also, Thuan, who looked into it, file processing programs.
Wonderful.
So, sorry?
Wonderful.
No, so there, these kind of constraints are there. But of course, the most common ones are length and checksum, the two that you mentioned. Those are the most common. Yeah.
I also like to add that we do not assume that the parser is recursive descent. So recursive descent is the standard parser, but actually Mimid works on control flow. So what it actually checks is whether a call on a so it also works if you have a big loop that simply processes one line after another. So it doesn't have to be recursive descent. What it assumes is some kind of control flow which it can observe.
Okay, so let's move to the next question. Thank you, Andreas. So there's a question from my colleague, Roland Yap. Maybe, yeah, I don't know, maybe Roland, you can unmute yourself and elaborate if you wish. I don't know if he's here.
Okay. So that's quite interesting work. I was just wondering, actually, the question is, how much can we say about extraction of the grammar? So the question is, suppose you take the simplest kind of grammar, at least in the language hierarchy, this would be regular grammars. Can we say that we can, we or you or whoever, can we say that this extraction can be done robustly? So or maybe this is more empirical question and we don't know how to answer this robust question.
Well,
so it might be a hard question to answer, by the way.
So there is still a big gap between what happens in a lab and what happens in practice. So our Mimid tool is a prototype, and it works on C programs and it works on Python programs. And this is because we have implemented dynamic tainting for both C and for Python programs. So that this is necessary in order to figure out where individual characters are being processed. All techniques that mine such input structure from existing programs need to have a means to inspect the program execution. There has been some work, in particular in the security domain, for analyzing file formats, in particular by looking at how loops process through individual files. This is sufficient for learning regular languages, but not sufficient for learning context-free languages.
So sorry, I think, if you talk about regular languages and in the extended
so in our case, if you have a tool that processes a regular language, then Mimid is going to produce you a grammar that then encompasses this regular language. Actually, if you look very closely into the elements of the grammar as we have them over here, you will already see that Mimid already has a couple of optimizations that allow it to express regular parts of the inputs that allow it to identify and to express such regular parts automatically.
Right, Andreas. But however, if one considers what people normally think of as a regular expression, and that is actually not a regular grammar, it's more powerful than regular grammar. It has semantic constraints in there.
Yes, that's true. It all depends on. So there's two answers to that. So first, plain regular expressions, as in regular languages, this is something that we subsume with grammars in the first place. And if the input language that you have is actually a plain regular language, then you can also convert the grammar into a regular expression of sorts, and then you have a regular expression that matches your input. That is pretty straightforward. If you do have an extended regular expression that then comes up with plenty of constraints on the input, if you take Perl regular expressions, for instance, at some point these are Turing complete. So actually there are examples of Perl regular expressions which are do they border undecidability? I think they do, where you can express anything that can be expressed in a Turing program. These are obviously things that we cannot mine from. These are obviously things that we cannot mine from a program, because the program itself is a Turing machine, and any abstraction that we could get out of there would be either extracting the Turing complete representation, or a gross oversimplification. So there will always be limits to what we can get out of there, but we also want those limits because we want to focus on a particular aspect of the program input, namely the aspect that is concerned with the program syntax, and also the program semantics, up to the point that we can generate as many inputs as possible. In principle, if you take this further, learning the language of failure, we may also be able to produce a program that produces inputs that only produce failures by extracting a slice out of the program, taking its semantic constraints and everything. But at this point, we are very quickly into scalability problems. You are the whole scalability problems of symbolic execution. You are in undecidability problems, and so you have to you have to find a thin line where you can still extract the syntax and the part of semantics of the input without getting too much of the whole program semantics into your representation, because at some point there are simply things which you would rather like to have your fuzzer cover, rather than trying to extract all of this into a model which then borders undecidability.
Okay, thank you, Andreas. So there's one other question, maybe we can take that one. So Adi, I don't know whether you're here. So yeah, so whether the learning of software behavior, it can be modified to use the oracles, so that you can use this for teaching, basically, teaching of programs. So Adi, if you have further clarifications, feel free to unmute yourself.
Hi. So yeah, so I was thinking whether it only works for grammars, or can it work for like general programs? Because usually for introductory programming, the programs are simple, but whether can you extract the kind of inputs that will make the student's program fails?
So as soon as you can model your input as a language, which can actually also be something like a function call, because a function call can also be expressed in a grammar, say you're having a function followed by an opening parenthesis, followed by an integer, followed by a closing parenthesis. This is also a grammar. And yes, if the program fails, then you can use this very technique to tell students, just as you do programmers, to give them an explanation under which precise circumstances their program fails. And then you also give them test cases that actually show why the program fails and when the program fails. And then they have much better material on their hands to actually fix the failure, which can be a great relief for students. But on the other hand, this may also diminish the learning experience, because obviously you want to teach your students to come up with such abstractions and to also come with such good test cases themselves. But indeed, it is my aim to automate lots of these things for regular programmers and possibly also for students.
Right, because part of the other problem is that when you are grading the students' answers, you want to give comments, right? I mean, they won't do it again, but if you don't give comments, then they will complain that you're
Yeah,
not.
that's correct. You can directly, rather than, so for you as an instructor, rather than having to figure out why is this not such a great solution, you can simply start this whole thing and then tell the students it won't work for these inputs and it won't work for this general case, and your fix is actually incomplete because it doesn't cover all that, because it doesn't cover the general case.
Okay,
Okay.
thanks.
Okay, awesome. So maybe we are, let's see if there are any other questions. Yeah. Probably not. So thank you very much, Andreas, for again sharing your insights. So there is maybe one other question if you want to take it, maybe
Yes.
one for the road. So one question if you want to take. So yeah, maybe let's have this as the last question. So the difficulty to mine semantic grammar of inputs like checksum constraints among input parts is to unable to track down many parts of inputs during taint analysis.
Yes. So the difficulty of tracking checksums is not so much to find out that a checksum function exists, but the problem here is, so we can identify that there's elements of the input which eventually flow into some function, and then we can identify that the output of this function, or the result of this function, is used to determine that that whether the input is valid or not. That's not so much the technical question. The big technical challenge is actually to extract such a function like checksums or length and likewise into a form that it can be evaluated and assessed independently of the program. So what we would like to have is a means to extract the checksum constraints, the checksum functionality, a functional description of checksum, in a form that it can be brought into the grammar, that it can be integrated into the grammar, and then whenever I am producing something from this grammar, I would be able to automatically also produce inputs with valid checksums. So when you're doing fuzzing, regular fuzzing, then what you would find out, oh, here is a function that does checksums, or let me just replace this function by something that returns true all the time. That's one of the techniques that you can do. But we want to be able to produce such inputs reliably, even for programs that we cannot change, and even for programs that you cannot cannot even inspect. See, the one advantage of grammars is once you have them, you can apply them to any kind of program that accepts this kind of inputs, even if you don't have access to its source, or even if you don't have access to observing its execution. And that's the major challenge: extracting those constraints and the functionality from the program into an independent representation that can then be part of your input language specification. And that's complex. Conceptually, it's okay-ish, but from an engineering perspective, it's a big challenge.
Okay, thanks, Andreas, once again for sharing these insights. Of course, I think this relates to a lot of the work that we are doing in testing analysis and also some work in security. So I'm sure we will have quite a lot to think about. Thank you. Thank you so much.
Been a pleasure. Thank you very much. See you.
So I will actually follow up on your ESSEC FSC paper, Andreas. Yeah, because this problem has always been there. Whenever there is a crash or a failure that is reported, what is the reason? What are the other inputs which fail for the same reason?
Yes.
This is always a bit tricky. Yeah, people use all sorts of things like stack traces and all, but that's not really suitable. Yeah.
So this is something which we only realized about when was that 18 months ago. So the thing is, the typical approaches to debugging look into or explain things by means of program features. That is, this variable had this value and this function was called and whatever. And it occurred to us that many of such explanations require you to actually have the entire context of the program in mind. Meaning that for me, the classic was the program failed, the program raised a null pointer exception because P had the value null. Yeah, well, that's not very surprising.
Yeah.
But where did P come from, and how? And so you still have to trace back all the way. And yeah, of course you can. There's ways you can do that, but all of these explanations require all the context there is.
But would it be, so I was wondering, probably it would be difficult to bring in relational constraints like X greater than Y, because the nature of the mutations, everything is being kind of inferred through mutations. So you are mutating maybe one field or one variable at a time. So something like length greater than 619 will be possible to infer.
So there's two answers to that. So the one thing that we realized is that actually that these grammars that describe the input actually are not part of the program domain, but they're part of the problem domain, and that changes a lot.
That's right,
because they relate. Because this means that this relates to things that exist independently of the program. So it gives you a domain that even you, as a non-expert about the program, may be able to reason about. That was one thing, and the second thing is, well, in the end. For our ESEC, for the Al-Hazen work, for the ESEC FSC work, we were very reluctant to add as many features as we wanted, because we did not want to over specialize the set of features towards our benchmark. So we very much took care to first select the set of features and then select the programs that we wanted to try out, and not do any kind of over specialization here. But in principle, you can actually go and do a daikon-like approach, coming up with plenty of features that also relate to, well, essentially you treat all these individual non-terminals like variables. And then you can come up with a feature like this element A is smaller than element B. This is what we observe. And here comes another one, and here comes another one. And normally, if you do such an explosion of features, then any machine learner, any expert in machine learning is going to tell you that's a very bad idea to do, because you have far too many features to choose from. You need to have fewer features to learn from. But since we do have this feedback loop, which specifically looks for further features to look at, and since with every new iterations, the learner automatically excludes features that simply are not relevant for the failure, we actually might have a good chance of doing that.
Yeah.
One thing that could be more difficult is that simply so if you look at, you may still run into into a combinatorial explosion of sorts. If you do relations between two variables, that might work. But if you do relations between three variables, well, and at some point, the set of equations that you can produce simply becomes far too large.
Yeah, but as you said,
but this is then where work like yours, for instance, could be very interesting.
Yeah, no, as you said, the iterative refinement would probably naturally take care of the explosion of feature. There is a possibility. Yeah. Thank you very much, Andreas. Yeah, it's always a pleasure to learn about the latest from your group. Yeah.
Have a nice afternoon, Abik. Have a nice evening and a nice weekend, I would say.
Yeah, and you too. Have a great day. Bye-bye.
Great to see you.